These are the solutions to the questions on satellite orbits, including geostationary satellites. So I don't think I've stated these are exam questions, but they're basically the same as that. They're really quite challenging. And I've got the marks here as well. So these are both probably grade A, grade B. So let's have a look at this first one. We've got a circular orbit. So we always assume it's a circular orbit, even though we know it's actually an ellipse. And we've got to show that question. So this is quite standard. So some exam boards will give you this formula, and some will ask you to derive it or expect you to memorize it, but it's a relatively straightforward derivation. So the key thing here, as we mentioned in the lesson, is that something needs to provide a centripetal force if an object is to move in a circle, and in this case it's provided by the gravitational force. So we can say that mv squared over r is equal to the force from Newton's law of gravitation, gmm over r squared, and we can cancel this a little bit. I tidy it up, so we've got a little m there, get rid of that, get rid of one of the r values. I can't seem to get rid of that, never mind. And that tidies up to v squared is equal to gm over r, and then hopefully we can see where that comes from. We just take the square root of both sides and we have our expression here, which is great. So relatively straightforward. Just remember, as always, if you're doing a derivation, it's got to be really clear. Now there's only 2 or 3 lines here, 2 lines I suppose, but it's got to be very, very clear. Do you have to write this text here? Probably not, but it has to be clear. If it's not clear, then obviously you will not get the mark. Part B, so following on from what we've derived here, so explain how this expression in equation A shows the relationship. So we could describe the relationship and then just talk a little bit about what's going on here. But we can see that big G and big M are both constants, so we can basically get rid of those from the relationship, and we can replace the equal sign with a proportional sign. So V is proportional to 1 over root R. So that will get you 1 mark. The second mark is just explaining what that means. So if we have a larger value of the radius, even though we're square rooting it, we are dividing by a larger number. So the bigger the value of the radius, the smaller the velocity. So we just need to state that in words. Satellites in higher orbits will travel more slowly, according to this expression. Right, part C. So we're given a radius of satellite A, a radius of satellite B. Determine the ratio. They really like these questions in year 2 A-level physics, especially in gravitational fields, working out ratios and then maybe making a comment on them. And if you're looking at this and thinking, I have no idea what's going on, it's always useful to look back earlier on in the question. They've given us this formula here for a reason, because we need to use that to answer part C. So that's always a useful tip. So we're trying to work out the ratio VA over VB. We could put that full expression in there, but the G and the M are going to cancel. So we end up with just 1 over root R. But do be careful here, because it's 1 over this expression here. When we work out this ratio here, then we're going to have RB divided by RA, because it's the reciprocal. So we've got RB over RA. We're given those expressions up here, hopefully. And then we can work out the square root of that. That comes out as 4. And so the square root is 2. So satellite A travels twice as fast as satellite B. So we wouldn't need to write that final sentence, but that's probably a good idea just to make it very, very clear what we have found out. Final part, part D. So a student states. Again, the examiners really like presenting you with an idea which may be correct or may highlight a common misunderstanding, and then discuss whether this is correct. And 3 marks, and sometimes these are for a lot more marks. So this is quite a tricky question to answer, but hopefully it should follow on from the ideas discussed earlier on in the question. So further from the Earth must move faster because it has a larger orbit. Well, it does have a larger orbit, but we've just said, well, it doesn't move faster because of this expression here. So we just need to go through and write sufficient information to get 3 marks. So we can acknowledge that it does have a larger orbit. Yes, it does. So it's further away. So the gravitational force acting is weaker. We can make a comment about that because it's further away. Because of Newton's law of gravitation, we can make a reference to that. And if we have a smaller gravitational force, then we're going to have a smaller centripetal force. So the satellite is going to move more slowly in its larger orbit. That'll probably get us a second mark. And then probably the most straightforward one, because this is the expression they actually gave us in part A. According to this expression here, the orbital speed decreases as the orbital radius increases. So there's a little bit of repetition here because this was also mentioned in part B. But we need to make a comment about this student statement. Is it correct or not? Well, it's incorrect. Even though it's a larger orbit, the velocity is lower because of this expression. And then for the third mark, we could make reference to the centripetal force and the gravitational force as well. So quite difficult to get 3 marks there for part D. So lots of detail needed there. Question 2. This is your really typical question, and we did this in the lesson. Calculate the height above the Earth's surface of a geostationary satellite. So this is a standard question using Kepler's third law. They might tell you what the time is, but they probably won't. And this often confuses students because they think, what's the time? I don't know what the time is. But we know by definition, if a satellite is geostationary, it must have the same orbital time period as one rotation of the Earth on its own axis. So that's 1 day. Therefore, we can work out the time period. It's the number of seconds in 1 day. 60 times 60 times 24. So very often students would lose out on this question because they forget or they don't know how to work out the time. Once we've got that, we can put the numbers into Kepler's third. I haven't got the full formula here. Don't know why that's missing, but we did see that earlier on in the lesson. So we've got t squared is proportional to r cubed, and we've got the gm and the 4 pi squared. So we can put the numbers in, and it's the cube root with the time and with g and with the mass. So we're given all of these in the question. So we can work out the radius, and that is great, 4.23 10 to the 7. Very often students would write that down and move on to the next question and obviously miss out on a mark because the question actually says find the height above the Earth's surface. So it's an extra step that we need to include. We are given the radius of the Earth, and we can convert this into kilometers or leave it in meters, and we get our answer there in kilometers or indeed meters. So we need to subtract the radius of the Earth from this answer here in order to get our third mark. Part B, calculate the ratio. Once again, they're finding, the question is saying find the ratio of 2 values. So we've got G at the surface, and we've got G at the satellite. What is the ratio? So we could calculate, well, we know the value of G at the surface, that's 9.81. So we could just calculate the value of G, and there's various ways we could do that. Or we could do this in one stage, which is what I've done. So we know that G is equal to gm over r squared. So this is related to Newton's law of gravitation, which is gmm over r squared, but the weight is mg, so little m cancels. But we are given this expression. Most exam boards will give you this in the formula booklet. So G at the surface is gm over r squared for the surface. G at the satellite is the same expression, but for the satellite. And we can see that the big G and the big M cancel. So we end up with r squared divided by r squared. Rather like we saw in question 1, because the r squared is on the bottom, we've got to be careful. That's going to be r squared surface on the bottom of the fraction. And then we're dividing by 1 over r squared here. So that will go up to the top. So r squared satellite goes on the top. So we should get our values here. I think the one we've got for our answer for part A, but be careful. Now we go back to the actual value from the center of the Earth, which is the 4.23 10 to the 7 squared. We know the radius to the Earth's surface. The radius of the Earth is 6,400 kilometers. So we can work that out as 43.7, which rounds to 44. So we could say that the value of G at the surface of the Earth is 44 times larger than the value of G acting on the geostationary satellite, which should not surprise us because it is a long way out. And we have this inverse square relationship between G and distance. Final question, final part is part C. So once again, we're thinking about what happens if we increase the orbit. So similarities to the first question. State and explain. So watch out for that. The state is just a statement or a description. the explain will get the second mark. So if it's 6 marks in total, and there are 3 things we need to cover, that's basically 2 statements or 2 comments for each of these. So let's have a look at the orbital speed. So it's worthwhile breaking this into the 3 parts. We've already covered this before in question 1. So this is basically the same. We've got our expression here, which we've derived or were given in the formula booklet. As radius increases, then v decreases. So the satellite will move more slowly in the higher orbit. What happens to the period? Let's have a look. So this is going to be Kepler's third law. According to Kepler's third law, really nice little expression according to this formula, according to this law. Good exam technique. So as r increases, the orbital period will increase as well. So the satellite is going to take longer to complete one orbit. So we kind of knew that already, but now we're actually making reference to a formula or a law in this case. What happens to the gravitational force? And this is going to be according to Newton's law of gravitation. We could say that GMM doesn't change. So as r increases, the gravitational force will decrease. That is an inverse square relationship. So it is a 6-mark question. Is it longer response? Kind of, but it's basically 3 statements with a little explanation about what is happening with velocity, time period, and force. So hopefully relatively straightforward. Good, well done. So those are 2 questions on satellite orbits and also geostationary. Hopefully that was useful, and you can move on to the next part of the lesson.